All right, here are just about three separate practice problems involving static friction, just a little bit more practice with the idea of static friction versus kinetic friction and some of the sort of nuances or tiny details we have to work with when we're talking about static friction. So first problem we have is a 50 Newton box is at rest on a horizontal surface. Coefficient of static friction between the box and the surface is 0.5, while the coefficient of kinetic friction is 0.3. And a horizontal 20 Newton force is exerted onto the box. We're wondering what the box's acceleration is. So first thing I'm going to do is draw a little free body diagram for myself. I got a little box, and I've got a 20 Newton force. Didn't tell me which direction, so I'm just going to assume that it's to the right. That is 20 newtons. And I've also got two more forces. I've got my weight, that mg, and I've got my normal force. Now the problem did tell me that my box is 20 newtons. That is the entire force of the weight, not just the mass. And to work back to the mass, I'm going to say that my weight is my mass times the acceleration due to gravity. So my mass is going to be 50 divided by 10, and that equals m, which is 5 kilograms. So I've got a 5 kilogram box in action right now. So I want to do two things first. Because I'm going to be working with friction, I need to know what my normal force is, because both of our friction equations for static friction, we're talking about the force of friction being less than or equal to the normal force times the coefficient of static friction. And for our kinetic friction, we've got that equal to the normal force times the coefficient of kinetic friction. So either way, if I've got a friction force being applied to a box or an object, I have to know what my normal force is. So I'm going to set up a net force equation. Net force equals ma. And I'm going to do that for the y direction. This is going to be for the y direction, and the y direction only. So in the y direction, I'm not accelerating at all, which means my net force has got to be 0. So the net force acting in the y direction is my normal force minus my 50 newtons, and that has to be equal to 0. My normal force is positive or upward. My weight is downward, that 50 newtons, which means that my normal force is also going to be equal to 50 newtons. So from here, I can go ahead and determine a couple of things. The first thing I want to do is actually erase some of this writing, just so I've got some extra space to go off of. Erase down here. And I'll just write that I've got a 5 kilogram box. First thing I want to do is determine if I have static friction acting or kinetic friction acting. So the first thing I want to do is determine what the maximum value for static friction would be. If the force that I've applied is less than that maximum, my box is not going to accelerate. So for the maximum for that static friction, it is where the friction force of friction is equal to normal force times mu sub s. This is my maximum, the maximum. So I'm going to look for that number. My force of friction there is going to be equal to my normal force of 50 newtons that I solved for before, times, from the problem it told us that the coefficient of static friction between the box and the surface was 0.5, so there's 0.5 there. And that means that I have a maximum of 25 newtons of friction force acting on my box statically without moving. And this 25 newtons is greater than the 20 newtons that I'm applying to the box, which means that my acceleration is going to be 0 meters per second. My box is not going to move. The force of friction, the force of static friction that can be applied matches up with the force that I'm actually applying. So the question then becomes, is the force of friction actually 25 newtons or is it some other number? and it's actually going to be less than that 25 newtons. Remember, the static friction is sort of the lazy version of friction. So the force of friction, as long as the applied force is less than my maximum, the force of friction is going to equal that applied force. Because my acceleration is going to be 0, my net force has to be 0. In order for that to happen, my force of friction minus my applied force, that 20 newtons, have to be 0, which means those two numbers have to equal each other. So my force of friction is going to equal my applied force, which is going to equal 20 newtons. It's important to realize that it's easy to just go through that calculation and get that 25, and when the question asks you for that force of friction, just saying, oh look, I calculated it to 25 and that's it. But we actually have to interpret what we've done here. We have to be able to say that yes, in fact, the maximum is 25, not necessarily the actual force of friction in that moment. So we've got a second problem, and it's very similar, this time just with an inclined plane, and we've got a 15 kilogram box that is sitting on a 15-degree inclined plane. If the coefficient of static friction is 0.33 and the coefficient of kinetic friction is 0.22, determine the force of friction acting on our box. So first thing I'm going to do for myself is draw a little diagram. It's going to be, we got a little inclined plane here with an angle of 15, and we've got a box on here. So instead of drawing a free body diagram where I've just got those forces labeled, in that situation we would have the force of friction with gravity pointing straight down from the box, mg, and a normal force again that is perpendicular to the surface. Instead of doing that, I'm going to back all of those out. I'm actually just going to draw the forces, draw more of a diagram for myself. It didn't ask me to draw a free body diagram, so I'm going to draw the actual forces perpendicular and parallel to the surface. We've still got the force of friction going up the ramp. It's trying to oppose that motion. We've got a into the ramp force of mg cosine theta, or cosine of 15 here. Down the ramp we've got mg sine theta, mg sine of 15, and we have that normal force acting. So we're going to go through the same process as we did in the first problem. First I want to decide, does my box move? Does the force pulling down the ramp, that mg sine 15, overcome whatever my force of friction is? So I want to know my maximum value, again, of my static friction. So my force of friction is less than or equal to the normal force times the coefficient of static friction. So at its maximum, these are equal. So I'm going to look for the force of friction that would be sort of the magnitude of it in that case. So my force of friction, really, this time I'm looking for my normal force times the static friction, what that is equal to. The coefficient is 0.33, and my normal force in this case is going to be equal to mg cosine theta. Because my box isn't accelerating off of the ramp or back into the ramp, my normal force has to be equal to that opposite force. So mg is going to be 150, had a 15 kilogram box, times 10 for the acceleration due to gravity, and the cosine of 15, I actually brought my calculator this time, and that is going to be 0.966. 0.966, there we go. So the maximum value for my force of static friction is going to be 150 times 0.33. I'm getting a value of 47.8 newtons. So this is my maximum force of friction. If this mg sine 15 is less than that, my box is not moving. If it's greater than that, my box is moving. So from here, I'm going to take a look at what this mg sine 15 is. So again, it's 150 times the sine of 15. 150 sine 15. And we are looking at 38.8 newtons. So my force of static friction matches up with that mg sine 15. I have enough friction to actually prevent this box from moving. Because of that, I have to do a little more interpretation of what the actual force of friction is. And it's going to be equal to that 38.8 newtons. Just because my maximum is greater than that, it doesn't mean that in this particular situation, the force of friction has to be that maximum. If it was, then my box would actually be accelerating up the ramp. And from your own experiences, you know that can't possibly be the case. If you just set an object on a ramp, it's not just going to start sliding up it. That would be quite unique, to say it one way. So let's pretend we had maybe a little bit different of an incline. Same coefficients of friction. Let me go ahead and write those. Coefficient of static friction. Let's say it's still 0.33. Coefficient of kinetic friction is going to be 0.22. But this time, let's have a ramp that is at an angle of, say, 35 degrees. Nice roundish number. So, same situation. I've still got my box on my ramp. Thusly, it's still going to be a 15 kilogram box. It's still going to have some force of friction. It's still going to be with a normal force, a mg cosine theta and mg sine theta. So this time I want to know what my force of friction acting on my box is, and then maybe even the acceleration from there. So again, I'm going to look at my normal force, mg cosine theta, times the coefficient of static friction, 0.33, and that is my force of friction statically at its maximum. Plug in my 15 for the mass, times 10, times the cosine of 35 this time. That number is 122.9 times 0.33. Gets me this time a force of friction that is equal to 40.5 newtons at its maximum. Remember, this is the maximum value that my static friction can take on. And my mg sine theta, the opposing force, the force that's trying to pull down the ramp, is going to be 10 times 15 times the sine of 35. And that is 86.03. I call it 04. I'll just leave it as 86 rounded. So at this point, we've got a force pulling down the ramp that is greater than my maximum static friction, which means that the box is not actually static, it's moving. So now we have to transition to kinetic friction. So the actual force that is acting on my box, the actual force of friction, is going to now be the force of friction is equal to the normal force again, but this time times the coefficient of kinetic friction. Because I know my box is moving, I've got a greater value pulling down the ramp than I do trying to stop it from moving. My box is going to accelerate down the ramp. So my normal force again was 15 times 10 times the cosine of 35. That's my normal force, and I'm going to multiply it this time by my coefficient of kinetic friction, 0.22. So we are now ditching this number. It doesn't come into play anymore, and instead we've got a force of friction equal to 27 newtons. And from this point, I can set up a net force equation. Now I've got numbers for all of my forces in the x direction. I've got, or sort of the parallel direction, I should say. So this is the net force in the parallel direction equals the mass times the acceleration in the parallel direction. My net force, I've got mg sine theta, and I'm going to say that that's positive just because I know that's the way it's moving, minus my force of kinetic friction, and that is equal to my mass times acceleration. So from here I just substitute in mg sine theta I found up above to be 86 right here, minus this force of friction, minus 27. My mass is 15, and I'm looking for my acceleration. So 86 minus 27 divided by 15 is 3.9 meters per second squared as my acceleration. And this process occurs again and again with these static friction problems. This is the real difference between the static friction and the kinetic friction. The first thing we have to do is check for that number. We have to check to see if static friction will come into play. If our force down the ramp, or the force that we're trying to move our object with, is less than that static friction, the box doesn't move and the force matches whatever force we applied, whatever force is trying to move the box. If it is a greater number, if our force that we're applying, or the force that's trying to move the object, is greater than the maximum force of static friction, then we transition into kinetic friction and work from there just like we had in previous problems. So the last problem we have is one that is off the homework packet. It's a little bit more involved. It's adapted a little bit from last year's AP test. They asked some different stuff with it, but this is a very good problem. If this one comes naturally to you and you can progress through it, you're in pretty good shape for the test this coming week. So the diagram to the right shows a box of mass m that's pushed with a force that we're calling T. Probably not tension, just because a rope placed that way wouldn't really work too well. But just some force T, you could call it F if you wanted. And that force is applied so that it is both pressed against a vertical wall and it's also sliding upwards along the wall. This is a situation where if you were holding a picture frame up against a wall and you're trying to decide if it's positioned right and you're pushing it against the wall, but you're also moving it up the wall. You're applying some angled force into it. And it is being moved at a constant velocity. So if you're following along on the homework packet, the first question asks us to add the force of friction to the diagram on the right. The question says that the object is sliding upwards, which means that the force of friction is going to point downwards for our force of friction. And then B wants us to write Newton's second law equations both for the horizontal directions and the vertical directions, with no numbers, just the variables. So for the x direction first, remember net force equals ma. And in the x direction, I've got this normal force, and I've got some component of this applied force T. So my x direction force is going to be the T cosine of theta. So the normal force is pointing to the left, and if you look at the arrow again, it's not a free body diagram, so the arrows aren't where we would normally see them with the free body diagram, but it is actually pointing to the right, so those are in opposite directions. I like to make to the right positive, so I will do that. T cosine theta is that component going towards the right minus my normal force, and that equals ma. And I'm going to go one step further. My object is not falling off of the wall or falling into the wall. It says it's being pressed against it, so it's not accelerating, which means that that also equals 0, which means that T cosine theta is equal to my normal force. And remember, normal force can be represented a couple of different ways. Whatever way the problem represents it, you should do that in the problem in your work as well. So for the y direction, we've got a couple more forces. Still net force equals ma. This time we've got our other component of tension. It's pointing upward, and that is T sine theta. Again, I'm not sure that's actually tension. It's just some force. We've got mg, and we've also got our force of friction acting there. And those all still equal 0. It says it's sliding at a constant velocity, which means that our acceleration is going to be 0. And then the next couple questions give us some parameters there, some numbers to plug in to determine what we've got going on here. So it says, what's the magnitude of the normal force? And it gives us T as 120, theta as 70, and M as 9 kilograms. I'm not going to write those out because we're going to get a little cramped. So please be following along in your homework packet so you can see where I'm getting those numbers from. So let's go ahead and substitute those in to this equation, the one that has my normal force in it. So it gave us a T of 120 times the cosine of the angle 70 degrees it gave us. It's going to be my normal force. 120 times the cosine of 70 is going to be 41.04, so I'll just call it 41 newtons is my normal force. And then it asks, what is the magnitude of the frictional force acting on our block? So we can go over to this equation here. T it gave us was 120 times the sine of 70 minus mg. It told us that the mass was 9 kilograms in the problem, so 9 times 10 is 90 minus the force of friction, and that equals 0. So a little bit of math here. 120 sine of 70 is 112 minus 90 is 22.76. I'll just call it 22.8 minus the force of friction equals 0, which means that my force of friction equals 22.8 newtons. And I know for a fact that this is kinetic friction. My box is sliding. That means it's moving, and we've got kinetic friction in this case. So the last question that it asks then is just for the coefficient of kinetic friction between the mass and the wall. So we know our force of kinetic friction is equal to our normal force times mu sub k. Force of friction we just got a second ago, 22.8, and our normal force is 41 newtons, and that is times mu sub k, so divide both sides by 41, and we get a mu sub k that is equal to 0.56. So hopefully these couple of problems have helped you guys solidify a little bit of those sort of loopholes that I had struggled to inform you about during class period. Again, I'm sorry for missing this past Monday. So hopefully this helped tie up some of those loose ends for those of you who are having troubles. We are going to have some time this coming week to practice them a little bit more in class and get more into AP sort of level, the test level questions, and questions that you are more likely to see than just the simple ones. You know, more variables like this one and more problematic, trickier ones, so you can get better looks at those as well. Again, thank you for watching. Thanks for putting up with me. Hopefully this is helpful. Enjoy the rest of your weekend, and I will see you all on Monday.